Good morning, guys. So we've tested the system. It works. It's working. All right, so you're still coming. So 10 a.m., so we can start. So what are we going to do today? We basically almost done developing a new approach to solve problems of electricity, right? So using scalar quantities. You remember we started like a few classes ago making a transition from vector quantities, electric field and electric force to a scalar quantity. So eventually we replaced force with the electric potential energy. Both of those quantities describes interactions between charged objects. And then we replaced electric field with the electric potential. Both of those quantities describes, again, the same thing, electrical aura around any charged object, right? Okay, so now, since both of these quantities, electric field and electric potential, describe exactly the same thing, it means there must be connection between them. So, in the previous lecture, I think it was yesterday, right? We derived those relationships between the electric field and the electric potential. So today we just need to practice them, right? And that's what we're going to do. But first, we just need to quickly review everything. Right? So during the derivation, what I've done, right? So I assume that there is some particle. Charged particle, right? And we moved it, or particle moved by itself. It doesn't matter. Right, from some initial point to some final point, completely arbitrary situation, right? And of course, it must be exposed to some electric field. Let's say this is some electric field, right? And we calculated work done. Of course, particle interacts with the electric field. Of course, there's work done, right? So we calculated that work. Work was replaced with the change in the potential energy, and of course potential energy can be connected with the electric potential. And on the other side we had an integral of f dot ds, and of course electric force can be replaced with the electric field. So that's how, and then charge can be moved to the other side, and we eventually got this. So first of all, I need to say that this is, okay, let me show the bridge. This is a transition from the electric field to the electric potential, right? Or usually, very often, I call it just a bridge, right? Bridge from the electric field to the electric potential, right? All right, and so using that idea of work, we derived this formula. So delta V, change in the electric potential, which is basically V final potential at the final point minus the electric potential at the initial point. Okay, let me write. So it's a V final minus V initial equals, okay, let me reduce this, equals negative integral from the initial point to the final point of E dot ds. ds, it's infinitesimal small displacement in the direction of motion, right? Okay, so that's general formula. You can apply it for to find the relationship between electric field and the electric potential in completely everywhere, right? But we need to adjust it for our simpler cases, which are going to be simpler, right? So in order to do that, I will do this. So I will just rewrite it slightly. So delta V equals minus integral of E cosine theta ds. I just dot product wrote explicitly through the cosine function. Of course, that is theta, right, between ds and electric field, right? And of course, what is this E cosine theta? If you take E and multiply by cosine theta, you will just get a component of this electric field. Let me project it. It's a component of the electric field along the direction of motion. So this will be E sub s, right? It's the component of the electric field along the displacement. So this is E sub s. And so as a result, it will be integral from of E s ds from s initial to s final. Okay, so, and now in our cases, all the time x axis is going to be s direction. So basically, one-dimensional situation we're going to discuss all the time, right? Because we're introducing physics on a very low level, on the simplest possible. Right? Okay, so let me write the final. So in our cases, x is s. Right? And so as a result, the formula, I will probably write it here. Should be, no, I will write it there. So it will be delta v equals minus integral from x initial to x final ex dx. That's what we will use in our classes. Again, delta, it's a potential difference between a final point and initial point, and you integrate it. And of course, yeah, if you feel comfortable with integration, write the function of E if you can, and integrate. We're going to calculate area because the graphical interpretation of an integral, if you plot E sub x versus x, then integral is just an area under the curve. Right? So if I plot E sub x versus x, and let's say the plot is, for example, all right, something like this. And let's say we want to find the potential difference, let's say, between this is x initial, and let's say this is x final. So what do we have to do? We just need to calculate the area under the curve. So it's this part and this. And careful, guys, right? If you calculate area, this area above x-axis are going to be positive. It's going to be positive. And this negative. Right? In your homework, there will be a problem where a part of the curve above, part of the curve below. So, of course, you'll have to take this and subtract that. Okay, and of course, so area under the curve, it's a minus delta v. Right? So, now let me write so. Area equals to minus delta v. So we're going to use this trick. We've done it in physics. You've done this in physics 1 when you calculated work done by the force, by a force. You calculated area, and there were some other cases, I forgot, right, where this trick was used. Okay, so that's a transition from the electric field to the electric potential. Now, how about opposite direction? So I will put a new bullet. And so now, how can we move from the electric potential to the electric field? And again, quite often I just call it, it's a bridge. Right. Okay, in this case it's easier. It's just a negative slope. If you plot V electric potential versus the x. Okay, so first I will probably write the formula. So let's start with the x component. Okay, so now we move from the scalar function to the vector function. Vector function has 3 components, so we must have 3 formulas for the x, for the y, for the x, for the y component, and for the z component. I have to watch my fingers. Sometimes I can show something right in the middle of the class, right? So E sub x equals to minus partial dv over dx. Strictly speaking, here should be a partial derivative, but since we are going to have usually a function of one variable, so partial straight derivatives are exactly the same, give us exactly the same. Right, so it's basically, if you plot v versus x, it's a slope, negative slope. Right. Okay, let me emphasize on that. So it's a negative slope. Right. Okay, So I will just frame this because that's what we're going to use most of the time. But of course, if you have also y component and z component, it will have exactly the same structure. E y, okay, it doesn't look like y. E sub y will be negative dv over dy, and of course E sub z negative dv over dz. But again, most of the time, our situations we're going to work along the x direction. And of course, in the vector form, all right, so you can write E, it will be, okay, minus dv over dx minus dv over dy, so that you would, again, realize it's a vector. So 3 components. Okay, and before we start looking at examples, let me just plot something completely arbitrary in order to practice this, the second bridge. So let's say I have plot v versus x. And I will draw just completely some arbitrary situation. Let's say these. Just completely arbitrary. And let's say I want to find, for example, the some information. Let's say some information about the electric field. Let's say at this point. Let's call it point A. So what do I have to do? Since we have information about the electric potential, I want to get information about the electric field, I have to use this, right? So I just need to look at the slope dv over dx and add minus. So the slope in this case at point A is positive and minus in front, so it means the electric field is going to be negative. What does it mean, negative electric field? Electric field is a vector. So negative, it means that it points in the negative x direction. So the electric field at this point is going to point, at this point is going to point that way. So E sub x. Then if, for example, let's say I take this point B, and let's say I want to get some information about the electric field at that point. The same, so, but now slope of the curve is negative, so dv over dx negative. So minus from there and minus from the formula. So it gives us positive electric field. So it means positive electric field, it just points in the positive x direction. So this will be the value of the direction of the electric field, right? It's one-dimensional and plus it's so. Then what will be the value, what can you say about the electric field at this maximum point? At the maximum point, slope is 0. So as a result, the electric field is going to be 0. So over here, right, let's say point C, so here E equals 0. The same here at the minimum, electric field is going to be negative. Oh, 0, sorry. Electric field is going to be 0. So by just looking at the slope, and don't forget about minus. Again, that's the major trouble usually when students use these formulas, right? About 20 or 30% of students usually make mistake with this silly mistake, right? With the minuses, right? Okay, so that's what I was planning to review. And now let's look at the problems. Problems today are not going to be complicated. So the first one. So the first one is, it's a chapter 26, problem 4. Right, and what is given in this problem? A graph. Electric field, how x component of the electric field changes with position. Right, so I will plot it here. Right, let me estimate the space. So this is E sub x, units of electric field. Up to this point, all the time we use what? Newtons divided by coulombs. And that's absolutely correct. But it can be easily shown that newtons per coulombs and volts per meters, exactly the same. Volts divided by meters, right? If we have time today, I will show you. So units, volts over meters. And the same as newtons per coulombs. All right, and let's say versus x. All right, so and then we have 1, I need 3. 1, 2, 3. So 1, 2, 3. And then 100 and 200. 200, 100. And the plot. So first, electric field stays constant up to 0.2. It's a dashed line, so it means it's not a curve. I just want to connect show that that point is just above 0.2. X actually is in meters. It's important, right? And I missed it. And then plot goes straight down to 3. Right. Okay, so that's the plot. And we need to answer the question. What's the value? So let me write, find V at x equals 3 meters. Okay, let me ask you, as much as I can, right? Again, during the normal semesters, right, all these questions really goes to students. If I leave the problem like this, nothing else added, will we be able to find the value of the electric potential at 0.3? First of all, we need to realize which bridge must be used. So we're moving from the electric field to the electric potential. So we need to use this bridge. It means that we need to use this formula. And look, this formula relates electric field with the change in the electric potential. So it means if I have that information about the electric field, yeah, I can integrate. But as a result, it will allow me to find the potential difference only between whatever points I pick as my initial point and my final point. I can pick, for example, this is my initial point, this is final, or this initial and that final. But I will never be able to find the value of the electric potential. Every time I would be able to find only delta V, potential difference. So that's why there is an additional part of the problem. Problem says, let's assume that the value of the electric potential, at the origin is negative 50 volts. And the same I gave you in the clicker question in the lecture yesterday, right? But at that point, I gave you the value of the basically the reference point. The electric potential at 0 point was 0, but now it's negative 50 volts. So what a big deal, right? So just we will have to crunch additional number, but conceptually it doesn't change anything. Right, so now let me write assume, because without this assumption, we will be able to find, only potential difference. So we have to make this assumption. Assume that V at x equals 0 equals to negative 50 volts. And again, guys, if something not clear in my handwriting, say something, right? Of course, I know you can chat and ask each other what did I write. So negative 50 volts. So now we should be able to answer this. So that's the, okay, let me emphasize again. So we're just moving from the electric field to the electric potential, and the formula, of course, delta V equals to minus integral from initial point to the final point, Ex dx. So direct application. And I want to also say one thing. If I ask you, what's the direction of the electric field? Is it, does it point along positive x direction? Okay, positive x direction or negative x direction? Since electric field, you see, it's a plus 200. What does it mean positive? It means it points in the positive x direction, right? If electric field would be, if the electric field were negative, then it would mean that the electric field points in the negative x direction, right? So in this case, it's all in the positive x direction. Right, so again, that's the what we need. And now, again, this you can apply for any situation, for any points, initial, final points, no restrictions except for its one-dimensional case. So we just we have to make a decision which point should we take as an initial point and which point should we take as a final point, right? So since, because of this assumption, some information is given about the electric potential at the origin, of course it makes sense to take this point as our initial point. And since we want to find the electric potential at this point, so it makes sense to take final point as a 3, x equals 3 as our final point, right? But of course the problem can say, okay, find the electric potential at point 2. Okay, in that case, final will be x equals 2. Right? It depends on the problem, what problem says. Or if I give you, let's assume v at x equals 1 equals negative 50. Yeah, in that case, you would take this point x equals 1 as our initial point. So it depends on the statement of the problem. Okay, so let me emphasize on this. So x initial, that's x equals to 0, and x final, that's x equals to 3 meters, right? So preliminary steps are done. So now let's write it explicitly, right? So delta V will be V at, okay, let me write just a subscript 3. 3 means x equals 3, V sub 3. Minus V sub 0. Again, 0 means x equals 0. Right? So I'm just opening this up. And it is equal to minus integral of ex dx. And now I will put the, oops, it doesn't look like 3. Let me fix it. And now we can write the limits from 0 to 3. And again, if you want, you can easily integrate it. Function e is quite simple, but we're going to again use the area. Right? So it will be minus area over, let me label this figure somehow. Let's say this is point O, this is point A, B, and C. So it's the area over that figure OABC, sort of like it looks like a trapezoid. Right? Area over figure OABC. Right? And of course, don't forget about the minus. Very, very typical mistake. Right. Okay, so now, of course, you can use the formula for a trapezoid, area of a trapezoid, but I will just split it into two, rectangle and triangle. Right? So it will be minus area over OAB. Let me label this point D as D point. Okay, so area of OABD and minus area of BCD, right, triangle. Okay, so now minus 200 volts per meters times 2, that's the area of that, so it will be minus 200 volts per meters times 2 meters, so that's the area of a rectangle. Area of a triangle, of course, don't forget about 1 over 2. And base times height. Base is 3 minus 2. So let me write 3 meters minus 2 meters. And times height. Height is, again, 200 volts per meters. All right. Actually, my idea was, I thought first about moving this to that side, but let's do this way. It's not a big deal. Okay, so let's calculate. It would be negative 400. This is 1. This 2 gets canceled, so it will be here 100, here 400. So it's a minus 500, right? So minus 500 volts. But again, that's the difference, delta V. We still have V naught on this side. So let's solve it for V3. V naught goes to that side. So will be V3 equals V naught and minus, and again, V naught with minus, but when I move to that side, it is with plus. And what we calculated, minus 500 volts. Okay, I need to restart the camera. So let me finish this. So minus 50, that's what is given, right? Minus 50, minus 500, minus 550. So that's the answer. So the electric potential over here, minus 50 volts, over here, minus 550, so the potential is going down. So the origin, not the origin, the reference point is somewhere over here on the negative side of the x-axis, right? But of course, we don't know where because we don't have information about what happens with the electric field on this side. So you see, this problem, not bad at all, right? And of course, if, like in the example which we discussed in the lecture, I wanted to find the function, how the electric potential changes with x. In that case, if the question is about finding the function, of course, you will have to pick some arbitrary x, not the particular point x. But in this case, since the question was about finding electric potential at this point, so we picked that point as our final point. Okay, so if something needs to be clarified, tell me, right? But usually, as I noticed, students usually don't have troubles after discussing this. Don't have issues on the exam or any tests. Of course, if a student practice it. Okay, then I will need to start erasing this slowly. So the next one is even easier. Okay, enough. Let's erase this. Okay, I will leave the last line. So now problem 11. And in your homework, you're going to have very similar, because usually problems in the book, they kind of pair it. The previous one and the next one are very similar, just like almost like a potato. So usually I try to solve one problem in the class, and the second one goes as a homework. All right, so problem 11, chapter 26. So in this case, what do we have? We have a plot, but now the electric potential, scalar quantity, versus the position. All right, so let me plot. I'm trying to estimate again the space. It should be enough. So this is the electric potential, units of volts, and versus x. And x is, in this case, is in centimeters, right? And again, pay attention to the units of x, right? Because again, that's another place where not many, but some made mistakes, right? Using wrong units at the end. Okay, so plot is given. So let's say this is, so let's call it negative 100. This is positive 100, and so then 10, 20, 30. So 10, 20, 30 centimeters. And the plot itself. So first, electric potential stays constant up to this point. Then after 20, again, it stays constant to point 30. And between them, we have a straight line. Probably I should show this also. So again, that's what happens with the electric potential. And you can see in this case where is the reference point. You remember, whenever you introduce the potential energy or the potential electric potential, every time you need to show where the reference point In this case, the reference point is over here where the potential is 0. So we want to get information, actually not get information, we just want to plot. We want to plot electric field versus x. Okay, now I can erase this. Right, so what is given? How v changes with x. So what we need to find, so we need to draw E versus x. Basically, that's what needs to be found. Right. Basically, art problem, right, about drawing. So we need to plot how this is x in centimeters, and this is E sub x, volts per meters units. Okay, so eventually we'll have to plot over here the electric field. How electric field changes with position, with x. Okay, so obviously, bridge, this one, must be used, right? So from the, we need to move from the electric potential, because that's what is given, to the electric field. Right. And one-dimensional case, so we don't need this and this. Right. We can assume that most likely this is 0 and this is 0. Right? So E sub x equals to minus dv over dx. Of course, when you go to a higher level classes, right, of electricity and magnetism, of course, this formula will look like minus partial derivative of v with respect to x, not a straight derivative. So that's the expression. And now, obviously, since we have three parts of the curve with sort of like a unique type of lines, right? So we need to divide this problem into 3 parts. This will be the first region, this will be the second, and that will be the third region, right? So we need to analyze them separately because slopes are different, right? So let's do that. So this will be the region number 1. This will be region number 2, and over here this will be our region number 3. Right. Okay, so let's start. You know what? I thought about squeezing it over there, but now I feel like I can do it here underneath. So let's start with region number 1. Right. So E sub x equals minus dv over dx. Right. Of course, you can tell me immediately. The slope is 0, right? So the electric field must be 0. Electric potential doesn't change, so it means that the electric field is 0. But you know what? I want to still, since this is the straight line, because we will need this, what I'm going to do now in the second region. Whenever you have a straight line, straight function, and if you want to find the slope using infinitesimally small displacement dx, can I also write like this, minus delta v over delta x for a straight line? Yes, it's only correct for a straight line, right? So if you have a straight line like this, like that, right? So if you calculate the slope using infinitesimally small dx or finite dx, the slope will be the same. But of course, it's true only for straight lines, right? So we use this quite often, right? So and now, of course, v final, this is v initial, exactly the same. Then, of course, the slope is 0, right? So 0. So I can plot, let me overlap these 2 curves. I mean plots. Right, so this is 10, this is 20, this is 30. So first, over this distance, the electric field is 0. Right. Now let's do the second region. So E sub x equals, and again, since it is a straight line, so we can replace minus dv over dx with delta v over delta x. Minus delta v over delta x. Right, so it's minus. And so what's the final point? Final point is here, at 20. Potential is 100. So it will be minus 100 volts. Then, because it's delta, so minus. And initial point, negative 100. So minus 100 volts. And divided by delta x. Delta x, 20 minus 10. And of course, we must convert into meters in order to get normal units of the electric field. So it will be 20 minus 10 and times 10 to the power of minus 2 meters. All right. So it will be 200 and another, oh my God, I'm getting 2,000. Yeah, negative 2,000 volts per meters. So it will be minus 2,000 volts per meters. Again, don't forget about that minus. All right, so then over this, it will drop. Let's say this is minus 2,000, and then the electric field stays constant. And then the third region, obviously, again, is going to be 0, right? Because the slope is 0. So that's the, you see, it's very, very simple. So E sub x will be, of course, 0. Slope is 0. So in order to move that way, you need to integrate. In order to move in the opposite direction, you need to look at the slope, right? Calculus. All right. You know what? Probably let's first solve this one, next one. Pure calculus. Okay, so I doubt that you have any questions, but if you do have questions, ask. So the next one, okay, I will start erasing at least the top. It's 14, and then there will be some conceptual question similar to what we had in the lecture. Right, so problem 14. So we have a function, how v changes with x. So v as a function of x equals to 100x squared. So what we need to find? We need to find electric field. Electric field at x equals 0 and electric field at x equals to what? 1 meter. Now, it's not a plot given, right? So we have, of course, you can plot its parabola, right? But now a function is given. So in this case, and what we have information about the electric potential. So the bridge which must be used, it's from the electric potential to the electric field, right? Okay. Okay, so we just need to differentiate it. Function is given, differentiation is usually the easiest work in calculus. So E sub x equals minus dv over dx, so it's a minus d over dx out of our function 100 times x squared. If we differentiate, it will be 2x times 100, it's a negative 200x. So that's the derivative. I'm sure that at this point you're comfortable with differentiation. Okay, so now just plug x equals 0 and x equals 1. That's it. It's something similar you're going to have in your homework. Right. So it will be 0, and Ex at x equals to 1 meters will be negative 200. Done. Right. That's why I kind of decided to finish it quickly before the conceptual question. It will take a little bit longer. Okay, so next one, yeah, as I said, will be conceptual. My neighbors probably hate these noises in the morning. Right. Okay, I will erase this. Right. Start erasing. I think it should. You have enough time, right, to digest it. Plus, again, it's just a pure calculus differentiation, right? Barely have any. It barely has any physics. Of course, plenty of physics, but in order to solve it, you don't need to know that. So, conceptual question 6. CQ. Conceptual question 6. From the book, at the end of the chapter, before problems. So we have an electron. No, first of all, let me show the plot. So what we have in terms of that electrical aura. So that aura is represented or described by this V, of course, units of volts, and let's say X, right? Let's say X is in meters, right? Maybe even I can put some numbers, 100 volts, minus 200, minus 100, right? To make it look better. In the plot, let's say the plot is like this, right? And then let's say this is point 2 and this is, okay, probably I should write it underneath, point 1 and 2. Okay, and now let's take an electron. So we'll have an electron. Okay, electron is released Yeah, for some people, electron is elementary particle, but when I was an undergrad student in that part of the town where the university was, our department, physics department, so we had a cafe named Electron, and next one, sort of like a also where they would sell some desserts. It was called Proton, right? Electron, Proton. Okay, town full of physicists, right? So we shouldn't be surprised to see that quirkiness, right? Okay, so electron is released from this point. Is released from point 2. Right, so that's electron is released from that point. And so we need to understand what happens to that electron, right? You remember we discussed that at the end of the lecture. And now I want to just repeat those steps one more time. Again, like in the lecture, I want to start from the very end. I just want to create like a skeleton of the question, of the problem, right? And then we will just go over that skeleton, putting pieces of meat to create this Frankenstein's creature, right, of the solution. All right, so let's start with the end. So basically, we need to know what will be the direction of motion, and is it going to accelerate or not? Okay, so at the very end, we need to answer the question about a direction. Direction of motion. Direction of motion. And as we discussed in the lecture, so in order to know information about the direction of motion, it's a pure kinematics, it's physics 1. And in kinematics, we had 3 levels kinematic quantities, position, displacement, distance. Then when you differentiate, you'll get to the level of velocities, average, instantaneous, whatever, right? And then the next level, if you differentiate one more time, you'll get to the lowest level of accelerations, right? And information about the direction is in the velocities. It basically tells you if velocity that way, it moves that way. Because in order to know the direction, you need to know what happens with position. If you know just the position at a certain moment of time, it's not enough. You need to know what happens with position in time in order to answer the question about the direction of motion. So that's basically the velocity level. Velocity level all the time gives us direction of motion. But in this case, the object, the electron, is released. So initial velocity is 0. And we want to know the direction of motion and immediately at the moment of release. So velocity level doesn't give us information about the direction of motion. So it means that we need to dive next to the next level, to the acceleration level, in order to extract this information. And of course, with the acceleration, you have to be careful because, like I explained in the lecture, if you drive in a certain direction and you press the brake, you still continue driving in the same direction, but acceleration will be in the opposite direction. So you have to be careful with the acceleration if you want to use it to find direction of motion. But in our case, since initial velocity is 0, direction of acceleration all the time, in this case, is going to give us direction of motion. If you stay in the car, if you start accelerating this way, that's your direction of motion. If you started accelerating this way, that's your direction of motion. Right? So it's in this special situation, acceleration is information about acceleration is enough. And maybe I will emphasize, right? So since v not equals to 0, so that's why we can use acceleration information about acceleration to get the direction of motion. Then, okay, now what do we need to know in order to get information about acceleration? Newton's second law, F equals ma. That universal law which can be used to describe motion of any system. So we need to know information about the force. And of course, in this case, it's an electric force. And which bridge we use to move from the force to the acceleration? Of course, Newton's second law, as I said. F equals ma. Okay, so now, in order to get information about force, it's electric force. We know the formula, that universal formula for the electric force, Q times E. So we need to know information about the electric field. So electric field, right? And as I said, in order to move from this point to that point, we need to use the formula which we introduced like in the second class of this semester. QE. Okay, and now to what we've been discussing today in order to get information about the electric field. And we can get information about the electric field if you have information about the electric potential. All right, so that's the initial step. So from V, we can move to the electric field. And of course, what we have to use this bridge. So it will be Ex equals minus dV over dx, right? So that's the skeleton of the problem. Right. And now let's quickly discuss it. So first step, okay, now we need to start from the very beginning, right? But sometimes in order to create this train of thought, sometimes it's easier to start from the end, right? So dv over dx, it's a slope. Of course, the slope at the point where the electron is. So the electron is there. Slope is positive, right? Slope is positive. So the slope is positive. Okay, maybe I show this. So the slope is positive. So the slope is positive, but minus in front. Maybe I should make it bigger. That minus looks small, right? But because of the minus, so slope is positive, minus, so it means the direction of acceleration is negative. Okay, we're almost done. Direction of electric field is negative. It means it points this way. So that's the direction of electric field over here. So that's the direction of the electric field. Okay, then force QE, charge is negative. So it means that force will be in the opposite direction. So direction of the force will be that way. So this will be direction of the electric force. And after that, mass can never be negative, cannot be negative. So it means direction of the force and direction of accelerations must be the same. So acceleration that way. So that will be also acceleration, right? And as we just discussed a few minutes ago, direction of acceleration gives us direction of motion. Right? So motion that way with a non-zero acceleration, because originally slope is not negative. As a result, electric field not negative, force not negative, acceleration is not zero. Why I'm saying not negative? Sorry, not zero. The slope is not zero, electric field is not zero, this is not zero, this is not zero. As a result, particle is going to accelerate, move that way with a non-zero acceleration, so velocity is not going to be constant. Okay, of course this question can be answered easily, but in a few classes we will discuss that option. But I like that we used in this question almost everything that we've discussed so far. That's why I like it. Okay, sorry for holding you extra 1.5 minutes. Not a big deal. You don't have to walk to another class.